Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. So this is the first day of the lecture of the new semester. So I really hope that you come with a very positive motivation and very positive determination to learn, especially when you are able to go back and to return to the university with a much better internet connectivity. Okay, so moving forward to chemical engineering thermodynamics, ECH 3120, we going to start with the first chapter, which is volumetric properties of pure substance. So in this chapter, we're going to cover four subchapter, which is pressure behaviors, volume and temperature. So I believe that you are very familiar with these two terms because in order to advance to chemical engineering thermodynamics, you should be able to have the knowledge of thermodynamics prior to that. And next one we have virial equation, and last one is power equation. Okay, there are basically three learning outcomes of the chapter. The first one is to define various thermodynamic terms which involve the pressure and behavior and the temperature, especially we're going to learn on the Pvt diagram. And next one is to determine the state of the system using cubic and virial equation of state. And the third one is to determine the state of a system using generalized compressibility tables. So basically, this is the chapter that will give you the guidance on how you want to use this table and this table, and table A and table B, and what are the difference. Okay, um, beforehand, the motivation of this chapter, in order to quantify the changes in the thermodynamic system, we have to be able to describe the substance which make up the system, right? So this is the basic and the fundamental of this chapter, whereby the substance is characterized by its properties. So we should really understand what are the pure substance and what are the properties before we are able to describe the problems in the system, right? So that is the main motivation of this chapter. Okay, first of all, we move on to the pressure behaviors. Okay, what is pure substance? A pure substance is a material with homogeneous and invariable composition. What does it mean? It means that it has the fixed composition throughout. And there are three main phases of the pure substance. The first one is solid phase, whereby the molecules are arranged in a 3D pattern or in lattice. And next one is liquid phase. The chunks of molecules float about each other but maintain an orderly structure and relative position within each chunk. And last one is the gas phase, whereby it is in random motion and high energy level. Okay, as I mentioned previously, that it has a fixed chemical composition throughout. And what are the examples of the pure substance? We have water. It can be a solid, liquid, and vapor phases. Second one is mixture of liquid water and water vapor, and carbon dioxide and nitrogen. And last one, mixture of gases such as air, as long as there is no change of phase. Okay, I want you to write down in the comment section below the question. Air is a mixture of several gases, but it is considered to be a pure substance. Please explain why. And make sure your answer is not copy paste from your other friends. All right? Okay. I give you 2 minutes. Okay, moving on to nitrogen and gases air. They are also pure substance because of what? Because nitrogen have a fixed composition throughout as well as air. So air, in order to know why air is a pure substance, even though it consists of a lot of composition, so please refer to the comment section below. Okay, the points to ponder. Okay, I have two tasks for you. Please determine the following, whereby the volume occupied by 20 kilogram of propane at 100 degrees C and 70 bar. And the second one is the pressure needed to fill a 0.1 meter cube vessel at room temperature to store 50 mole of propane. Okay, so I will give you, I think 5 minutes, right? Because it's just a simple one equation. So I'm giving you a hint. I believe that you have learned this equation very frequently previously, especially during thermodynamics. Okay, because it involves gas, so use the equations. And please mention why all this information are important and essential to the thermodynamic system. Okay, so put the answer in the comment section below too. I will check it out. Okay, we move on to the closed and open system. Okay, in one thermodynamic system, it can be a closed or it can be an open system because it is subjected to the surrounding also, and it involves the boundary, whether the boundary is fixed or movable, whereby for the closed system, only energy can flow, whereby in the meantime for the open system both mass and energy can flow. So basically, remember, if there's a question or there's a solution or the problem regarding the closed and open system, make sure if it mention only closed system, then only energy can flow, so mass does not flow in the closed system. So moving on to the properties of this system, thermodynamic properties consist of pressure P, volume V, temperature T, internal energy U, and enthalpy, as you have learned previously, which is the first law, and the entropy, which is the second law. You still remember what is the first law and what is the second law? Okay, put your answer in the comment section below. And for the intensive properties, for example, as listed previously, whereby the pressure, temperature, and volume, and extensive properties are the volume and UH properties. And the specific properties, we can just put it into per kilogram because it is specific to the to this kind of property. For example, right, specific volume. Then for this one, it should be specific volume because it is meter cube per kilogram. But if this only volume, then meter cube. But it is specific meter cube per kilogram.
When you study chemistry, there's a lot of things that come up when you're making measurements, and we'll refer to it being an intensive or an extensive property or variable. And what we mean by these is we really mean it's a property that changes with amount, or it's a property that's more intensive, which doesn't change with amount. And right there is really what your definitions are. Any property that you can measure that as you change the amount of substance, but that property doesn't change with the amount, is called intensive. A really great example of this is temperature. It's one of our premier intensive variables, if you will. Great example.
Right, so it is very clear. According to the definition, that intensive is the properties that does not change.
With amount. And right there is really what your definitions are. Any property that you can measure that as you change the amount of substance, but that property doesn't change with the amount, is called.
So this is intensive. Intensive does not change, but if it is extensive, then the property does change if we change the amount of substance. Like this one, right? Because we can see intensive, our example is pressure, temperature, and volume, because it does not change, but for the mass or volume, it change with the addition of the volume.
Thermochemical equations. Wow, how fancy is that? Can you imagine All right. Of a system. I prefer short words. I would like to call it chaos. The more chaotic, the more entropy. And enthalpy talks about the energy content of a system. Well, in chemistry, you have initial state and a final state. We normally call the initial state the reactant side, thermochemical. So a positive number, positive.
So this is just a small recap. That entropy refers to the randomness of a system, and enthalpy is the energy of a system, whereby you can find it from the final and the initial state of the system. And next one is state at equilibrium. The state of a system is the condition in which we find the system at a given time, and whereby two systems comprised of the same substance and intensive properties are at the same state. Okay, what are the intensive? Pressure, temperature, right? Which does not change. And the state postulate is the state of a substance in a system can be determined by two independent intensive properties. Okay, I refer back to the previous definition of intensive properties. Okay, the series of states through which a system passes during a process is called the path of the process. The value of thermodynamic properties of a system do not depend on path, only on the state of the system. And equilibrium is when a system does not undergo any further changes because there is no net driving force for change. For example, is mechanical, thermal, phase, and chemical equilibrium. Okay, next one is process and property diagram. The change a system undergoes from one equilibrium state to another is called a process. For example, expansion process, and it can be adiabatic process, it can be isothermal process, it can be isobaric process, and it can be isochoric process. Okay, for the isothermal, it is the constant temperature, isobaric is the constant pressure, and the rest follows. Okay, we move on to the Okay, I believe that you should be able to tell me the difference of isobaric, isovolumetric, isothermal, thermal, and adiabatic in the comment section below. This is the hint, and you can give your comment in the comment section.
Well,
Okay, the Pvt behavior of a pure substance can be better described by the property diagrams for phase change processes. The property diagrams help to study the variations of properties of pure liquid fluids when the change in phase occurs. Okay, what do you understand by this? Okay, what the statement implies that the pressure, volume, temperature, behavior is the most important characteristic of a pure substance, which can be described by several property diagrams that makes up the Pvt behavior for the phase change process. Okay, and the best known property diagrams are Tv diagram, Pv diagram, and Pt diagram. And please change. Okay, phase of okay. We go on to the example. Phase change process of pure substance. Consider a piston cylinder containing water. So we can see here, the pressure is constant, and we just add heat, or we just increase the heat, the amount of heat. Whereby this is the sketch of experiment in which heat is added isobarically, like constant pressure, into water in a closed piston cylinder arrangement, right? So we can see the difference occurs in the what can you imply from this? Okay, okay, you can give your comment. You can give your idea from the comment section below. So you can see here the first thing that you can observe is the state of the system. The state of the water itself. Okay, we start from liquid water. until it become water vapor. So that is the importance of us to understand the correlation between pressure, temperature, and also volume, because it is interrelating. All right. So as for this, according to this sketch, the more heat that you apply, so it will be the temperature, of course, will be higher, and the state of the substance change also. So this is the property diagram. So because of the phase, because previously, right, you mentioned that the Pvt diagram can better describe by property diagrams for phase change process. So we can see here, this is the phase change process from liquid water, saturated liquid water, or vapor liquid, saturated water vapor, and water vapor or supercritical water vapor. Okay, so this is the main background or the general ideas of this Pvt diagram. Sorry, Pvt behavior. Okay, another approach of it is in specific we can see this is different story, yeah, but the same connotation. You can see that if you add more heat, uh, the liquid will be more compressed. The liquid will be in the compressed state. This is the point that no, sorry, you don't increase the temperature. So in this point, the temperature, for example, 25 degrees C, the liquid is not about to evaporate because it is at just like the room temperature, and it is in compressed liquid state. And if you put on more temperature to 100 degrees C, then it will be about to evaporate. Whereby when the heat is added and evaporation starts as you boil the water, for example, and this is the point that it will become the saturated liquid. And next one is if you add more heat, then the evaporation continues, and but the temperature does not change. So this is the point whereby the saturated vapor and saturated liquid coexist, or it is called as wet steam. Even though in the naked eyes we can see almost the same, but actually there are very distinctive difference when it comes to thermodynamics. And last one is all liquid evaporated, whereby it is about to condense if you put on temperature, whereby the heat is removed, and this is the condensation process occurs, and this is the point that saturated vapor phase. And last one is this is the point that it's not about to condense and the heat is increased and it becomes the superheated vapor phase. Okay, so this is in a nutshell, whereby the temperature and the volume. Okay, yeah, this is in the proper proper diagram representation, right? From the compressed liquid, it become the saturated mixture, and then it become superheated vapor until it cannot be changed into the previous uh, state of the substance. So this is the point of the state 2. Sorry, okay, the first one, okay, let go into detail. Water exists in the liquid phase, whereby the compressed liquid, it is known as compressed liquid or subcooled liquid, and a substance that is not about to vaporize. This is the first point, whereby the temperature is only 20 degrees C. You just put a little heat. Next one is state 2. Water exists as a liquid that is ready to vaporize, whereby this is the point of saturated liquid. You have to really understand, right? What is saturated and what is what is supercritical and what is superheated, because you have to deal with the different types of table in this course. Or it is called saturated liquid, a liquid that is about to vaporize but not yet vaporized. So the state 3 is, this is the point, saturated mixture. As more heat is transferred, part of the saturated liquid vaporized. This will become saturated liquid vapor mixture, right? So if you can see that the difference or the condition physically, you can see the presence of water and the vapor coexist. Okay, the state 4, this is the state 4, this is the point. At 1 atmosphere pressure, temperature remains constant at 100 degrees C until the last drop of liquid is vaporized. So this is the point of saturated vapor, which is the last drop of liquid that is vaporized before it becomes the superheated vapor at state 5, whereby as more heat is transferred, the temperature of the vapor starts to rise. Okay, so this is the general representation uh, of the heating process of water at constant pressure. Okay. This is also the different thing. This is also the similar thing, whereby we put on the work to increase the temperature. Okay, next one we have Pvt diagram. Okay, what is Pvt diagram? Okay, if you try to understand this diagram. I'm not sure whether this is the first time you take a look at this diagram or not, but I give you like 30 seconds. Okay, all right. So, what is the first thing that you can see? You can observe this, right? Is actually the combination of PV, this point, this graph, this this diagram, PV and uh, PV and TV. Sorry, PV and PT. Yeah, PV here, PT here, and TV here. So this is the combination of three diagram that is commonly associated with the PVT behavior. Okay, from this point, what can you observe? Okay, I want you to answer in the section below. Please explain the steep curve of solid and liquid region of the PVT diagram. Okay, this is, if you can see, this is the steep one. This is the steep the steep surface of solid and liquid. If you can see, right, the difference between this and this one, the gas is not stiff. It's not steep at all. So what can you translate from this? Okay, so the point is, solid and liquid, can they be compressible? No, right? Okay, so that is the point. If let's say you try to compress the solid and liquid, it will not change. What does it mean? The volume does not change. So that is why the diagram is really important. It describes everything that happens to the substance. Okay. Okay, next one is okay, let's say we have this point. We have this point, and for the temperature, sorry, this point for the temperature, and we have this point for the pressure. Okay, this one for the pressure. So the pressure must be here, right? As the temperature, if let's say temperature is here, sorry, I think, okay, let's say the temperature is here. Sorry, the temperature is here, and then the pressure must be around here, around here, around here, and then no, not around here. I mean the point. The point should be here. And what happened to the volume? The volume should be here, right? Will it be if let's say the temperature is here and the pressure is here and the volume can it be here? No, it cannot be that point because that is that is why that is why the line denotes, right? Because the behavior described through each line, right? For example, this line or this line. So it cannot be like this. It cannot be like this, which is totally illegitimate. All right. Where's the eraser? Okay. So those are the points. Those the that is another point about the Pvt diagram. Okay, last one is what does it mean by this? What does it mean by this gray sheet? This one. What is this? Okay, why the point stops here? Why? Okay, an answer? Any guesses? Okay, because actually this is very simple. This is just a boundary, right? Actually, it can be as long as you want, but this is the boundary whereby it stops here. So that's why there's no value given here, no value, right? Okay. Okay, let's move on to the. Okay, I want to show you. I hope this video will not be blocked by YouTube because I want to show you the triple point of water. So the triple point occurs where the solid, liquid, and gas transition curve meet. Ice water is placed inside a vacuum chamber and turned on to lower the pressure. So it doesn't take long. Actually, it takes quite some time because, of course, right, it's not easy to turn into or to coexist for solid, liquid, and the gas phase. Okay, at this point, the water is starting to boil, like uh, we previously described just now on the curve. Okay, it's about time. Okay, the water is now at the triple point. So this is the triple point. The temperature and pressure are at the point where all three phases, whereby gas, liquid, and solid of the substance coexist in thermodynamics equilibrium. Right? This is really interesting, right? Whereby you can see it is melting, it is freezing, and it is boiling at the same time. You see? Wow. That is really impressive. So this is the so this is the triple line. The triple line. No, sorry, not this one, only this one. Only this part. Hey, no, this one. Where's my pen? Okay, only this one, triple line. So this is the point that liquid, solids, and gas can coexist. Okay, moving on to the Pvt diagram. Pvt diagram can be described through the process that has been previously described previously, whereby if the pressure is higher than this pressure, Tp pressure, it will be melting, and after that it will be evaporation. And if the P is lower than Ptp, then it will be in the sublimation forms, whereby evaporation directly without melting first. Okay, so basically this is, I think this is, you are really familiar with this Pvt diagram, because from solid it becomes liquid and it becomes the vapor. Okay, so but take note that there are basically substances that expand on freezing, for example, water, and the substance that contract on freezing. Most of the things are most of the substance contract on freezing. Okay, so for the critical point, I would like to highlight a little bit on critical point, because this is the point whereby if the water has reached this point, which is in the supercritical vapor, it will not be able to be converted into liquid. Okay, what is the example? The example is the drying process. If you, I believe that you you are familiar with drying process, right? So drying process is the process that the moisture escape to the atmosphere, whereby in this point, for example, in the oven, it has reached the critical point. So this is the point that all the moisture will be removed and it cannot be returned back to liquid. So that is the principle of drying process. Okay. Okay, next one is PV diagram. So PV diagram, you can see here, actually PV diagram and PT diagram is almost equivalent, but just different representation, and because of the different axis, obviously, right? So actually this is V. Okay, this is V. This is T. Right. Okay, this is V and this is P and V. Yeah. Okay. For this situation, okay, I just want to show you the difference. If let's say we take this 1 point, 1 P1 and P2. Oh, P2, and we take the delta P and delta 1, sorry, the delta P of this this one condition, and delta P for this one condition, this one at equivalent delta P. Yeah, I'm sorry for the writing. Okay, for P2, okay, just assume that the delta is equivalent, the same. But if let's say you try to interpolate this one, you can see that you can see the volume of this at a compressed liquid is smaller, the changes of the volume is smaller than if you interpolate this to this. So you can see, right, it's much bigger. Okay, that is meant by this PV diagram. And one more thing about the PV diagram is, yeah, again, this is the point of saturated, liquid, and vapor region, and this is the point of saturated liquid line and saturated vapor line. So this is basically describing the behavior of the substance for the pressure and volume. Okay, but this one is different. For PV diagram of substance that contracts on freezing, this is different behavior because we can see that uh, the presence of the different phases before it become into vapor. Right, for this one, it will become from compressed liquid to vapor, superheated vapor, and this one from solid to vapor. But this is not really significant to the topic. Okay, next one we have a TV diagram. So TV diagram explain about the point whereby it is the temperature and volume. If you increase the temperature, this is also the same, right? If let's say you can see the delta of T and delta of temperature, the same delta for superheated vapor will give you more volume. So it shows that the small temperature change in the compressed liquid will give lower volumetric change in the compressed liquid compared to the superheated vapor. So the rest are still the same, the saturated liquid line and saturated vapor line. So this one will be deliberated further through your table, saturated table that we will explore more after this. So this is for the PV diagram. Okay, sorry. Oh, this is the same one. This is the same one like previously. Okay, so that's all for this session. We will proceed with the table and using the table and yeah, the types of table and how to use it and how to read from the table and the virial equation and the power equation. All right, so thank you for your time, and we will see you in the next video. Thank you.